Particular solutions for homogeneous equations. Welcome, everyone. Let's begin our lesson on particular solutions for homogeneous equations. Now, if you look at the first slide, I want to start by connecting this to what we have already covered. In our previous lessons, we focused on the mechanics of solving homogeneous differential equations. By the end of those sessions, you were able to derive what we call the general solution. But what does that general solution actually represent? When you see that arbitrary constant, which we denote as capital C, in your final equation, you aren't just looking at one single line on a graph. Instead, that constant C means you are looking at a family of curves. Depending on what value C takes, you get a different curve, and together they form a whole collection of possible paths. However, in the real world, whether you are studying physics, engineering, or even economics, we are rarely interested in every possible path. Usually, we have a specific starting point or a known measurement. We aren't looking for a whole family of curves. We want the one, single, specific curve that passes through a particular given point. When we use extra information to pin down that one specific curve and find the exact value for our constant, we call this the particular solution. Over the next few slides, I will show you exactly how we move from that broad family of curves to finding that one unique solution. Understanding the concept. Think about it this way. A differential equation, by its very nature, describes how a quantity changes over time or space. Because it only describes the rate of change, the general solution we found in the previous slide actually tells us all the possible ways that change could unfold. It's like having a map of every possible path a car could take without knowing where the car started. To narrow this down from an infinite number of paths to a single, unique solution, we need some extra information. In mathematics, we call this initial conditions or boundary conditions. An initial condition is typically provided to you as a specific point, which we can denote as x0, y0, representing a point that our curve must pass through. Mathematically speaking, this simply means that when the value of x is equal to x0, the corresponding value of y must be exactly equal to y0. By taking these specific, known values and substituting them into our general solution, the one containing that arbitrary constant c, we can perform the algebra necessary to lock that constant into place and determine its exact numerical value. This is the bridge that takes us from the general family of curves to the specific particular solution we are about to learn how to calculate in the next slide. Now that we've established that a general solution represents a whole family of curves, let's dive deeper into the concept of how we pick just one. Step-by-step procedure to find a particular solution. Now that we understand the difference between a general family of curves and a single, specific curve, let's look at the roadmap for solving these problems. To find a particular solution for a homogeneous differential equation, you don't need to guess. You just need to follow these 5 manageable steps. Step 1 is the most important. Find the general solution. Since we are dealing with homogeneous equations, you'll start by using the substitution method, either replacing y with v times x or x with v times y. This transforms the equation into a separable form. Once you've separated the variables, you'll integrate both sides to obtain your general solution. At this stage, your answer will still contain that arbitrary constant, which we call capital C. Step 2 is to identify the given conditions. Look closely at the problem statement for any specific information provided. You are looking for a specific point, which we denote as x0 and y0. Think of these values as the key that will allow us to lock the constant c into one specific value. Step 3 is to substitute the values. Now, take that general solution you found in step 1 and replace every instance of x with x0 and every instance of y with y0. Step 4 is to solve for the constant c. Once you've performed the substitution, you'll be left with an algebraic equation where c is the only unknown. Use your algebraic skills to isolate c and find its exact numerical value. Finally, step 5, write the final particular solution. Don't stop once you find c. To finish the problem, you must take that numerical value you just calculated and plug it back into your general solution. This final equation, which no longer contains the arbitrary constant, is your particular solution. We are going to put this exact procedure into practice in the next slide with a worked example, so keep these steps in mind. Worked example. Take a look at the problem presented here. We are asked to find the particular solution for the differential equation, di by dx equals the quantity x plus y, all over x, given the condition that y equals 2 when x equals 1. To solve this, we'll follow the 5-step procedure we just discussed, starting with step 1, finding the general solution. First, we need to verify if this equation is homogeneous. If we divide both terms in the numerator by the denominator, the right side becomes 1 plus y over x, because the right side is now expressed as a function of y over x. We can confirm it is indeed a homogeneous equation. Now, to solve it, we'll use the substitution method we learned previously. Let's let y equals v times x. If we differentiate this with respect to x, we get di by dx equals v plus x times dv by dx. Next, we substitute these expressions back into our original equation. This gives us v plus x times dv by dx equals 1 plus v. Now, let's simplify. If we subtract v from both sides of the equation, the v terms cancel out, leaving us with just x times dv by dx equals 1. From here, we need to separate our variables. We'll move the x to the other side, which gives us dv equals 1 over x times dx. With the variables separated, we can proceed to integrate both sides. Integrating dv gives us v, and integrating 1 over x with respect to x gives us the natural log of the absolute value of x, plus our arbitrary constant, so we have v equals natural log of the absolute value of x, plus c. But remember, we can't leave our answer in terms of v, we need it in terms of our original variables. So, we replace v with y over x, which gives us y over x equals natural log of the absolute and x, plus c. Finally, to make it cleaner, we multiply the entire equation by x. This leaves us with our general solution. Y equals x, multiplied by the quantity natural log of the absolute value of x, plus c. Now that we understand the theory behind finding a particular solution, let's put it into practice with a concrete example. Now that we have successfully found the general solution, we can move on to the next slide to use our initial conditions to find the exact value of c. Worked example continued. Starting with step 2, we need to identify our given conditions. Looking back at our original problem statement, we were told that y equals 2 when x equals 1. This gives us our specific coordinate, or our initial condition, which we can write as x naught equals 1 and y naught equals 2. This is the specific point that our curve must pass through. Next, in step 3, we perform the substitution. We take these specific values and plug them directly into the general solution we just found. So, we replace y with 2 and replace x with 1. This gives us the equation, 2 equals 1, multiplied by the quantity natural log of the absolute value of 1, plus c. Moving to step 4, our goal is to isolate and solve for the constant c. This is where a bit of logarithmic knowledge helps us. Since the natural log of 1 is equal to 0, that entire first term inside the parentheses simply vanishes. This leaves us with 2 equals 1, multiplied by the quantity 0 plus c, which simplifies beautifully to just 2 equals c. So, we have found that c equals 2. Finally, in step 5, we arrive at our destination, writing the particular solution. We take that numerical value we just found, c equals 2, and substitute it back into our general solution formula. This transforms our family of curves into one single, unique equation. Our final particular solution is y equals x, multiplied by the quantity natural log of the absolute value of x plus 2. We have successfully moved from a general formula to a specific solution that satisfies our given point. Now that we have successfully derived the general solution in the previous slide, we move on to the final stages of our problem. Real-world application context. Now that we have mastered the mathematical procedure for finding a particular solution, let's step away from the abstract algebra for a moment and look at why this actually matters in the real world. In fields like physics and engineering, particular solutions are absolutely critical. You see, a differential equation is essentially a rule for how something changes, but it doesn't tell the whole story on its own. For example, imagine we are using a differential equation to model the trajectory of a projectile, like a launched rocket or a thrown ball. The general solution we worked with in the previous slides would represent a whole family of possible paths. Essentially, every possible arc the projectile could take depending on how hard it was thrown. However, in a real experiment, we aren't dealing with infinite possibilities. We know exactly where the projectile started, perhaps at the origin, which we represent as the point 0, 0. By using that starting point as our initial condition, just like we did in our worked example, we can move from that broad family of curves to find the one and only particular solution. This specific equation describes the single, unique path that our specific projectile actually follows. This connection between math and reality is vital, but as we move to the next slide, I want to make sure you don't let any common algebraic traps get in the way of reaching that correct solution. Common mistakes to avoid. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the concept of particular solutions, it is very easy to lose marks due to small, avoidable errors. Let's look at these common mistakes to avoid. First, watch out for substituting too early. I often see students trying to plug in the given values for x and y before they have actually finished the integration. Remember, the initial conditions are meant to find the constant c. Therefore, you must complete the entire process of finding the general solution, that is, performing the integration, first. Only once you have that general solution should you move on to solving for c. Second, don't forget to substitute v back. As we saw in our worked example on the previous slides, when we solve homogeneous equations, we use the substitution y equals vx. This often leaves your integrated result in terms of v before you attempt to plug in your initial conditions. You must replace every instance of v with the fraction y over x. If you skip this step, your final answer will be mathematically incorrect. Third, be mindful of logarithmic errors. In many of these problems, especially the one we just worked through, you will encounter natural logs. A very common mistake is assuming that the natural log of 1 equals 1. Please remember, the natural log of 1 is exactly 0. Keeping this simple fact in mind will save you a lot of trouble when isolating c. Finally, stay vigilant against algebraic slips. When you are isolating the constant c, the algebra can sometimes get a bit messy, particularly if your general solution is implicit. For example, if you have an expression like the natural log of y over x equals the natural log of the absolute value of x plus c, take your time with the algebraic manipulations to ensure you don't make a sign error or a grouping error. If you can avoid these 4 traps, you'll be well on your way to mastering this topic. Now, let's quickly review the key takeaways from today's session. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear. First, remember that the general solution is essentially a family of curves. Because it contains that arbitrary constant, c, it represents all the possible paths the equation could take. Next, we have the particular solution. Unlike the general version, this is a single, unique curve. It is the one specific path that satisfies a specific point, which we denote as x0, y0. To find this unique path, we rely on the initial condition. These are the specific, given values of x and y that we use to lock our constant, c, into place. Finally, if you ever feel lost during a problem, just remember this simple 4-step process. First, solve the differential equation to find the general solution. Second, substitute your initial values into that solution. Third, calculate the numerical value of c. And fourth, finalize your equation by plugging that value of c back in. If you have mastered this workflow, you are well on your way to mastering homogeneous equations. Great job today!